Ladies and gentlemen, this class recording has started, so if you say anything stupid or inappropriate, it will be caught on recording. So please refrain from doing so, unless you want to.
Maybe we want to be extra.
All right, so first things first, let's start off here. Calendar. Yesterday, I'll zoom in here. If you're on the class recording, you don't get to zoom in, but. All right, yesterday we watched a portion of Magic School Bus Makes a Rainbow. We did not finish it, but we got the gist of it. I will consider let you guys finish it on Monday because, as you'll see here on the schedule as we fast forward here, Monday I have set aside for reviewing this unit on mechanical waves, electromagnetic waves, and light in preparation for our test, which is scheduled for Tuesday. So, on Monday, if we have questions, you want to take care of those things for reviewing for your test, that's fine. But if we've got some time, then we can finish up on Monday. So, okay? All right, but today, I wanted to get through the last portion of this unit, the part on electromagnetic waves, especially the part on light, dealing with color. So a lot of the topics that you saw yesterday in the Magic School Bus video, we're going to visit again, talk about why they happen, all those good things. Okay? Then we review Monday, test on Tuesday. The objective sheet is posted. If you have not gotten yourself a copy of it yet, probably a good idea to do so. Okay? It's not quite as long as the last one. Test won't be quite as long as the last one. I was working on it this morning, but I haven't finished it yet. So I'll probably have it done by the end of the day. Not that it'll help you guys, but so.
How much points will it be?
I haven't finished it yet, but we're probably like 30-ish, something like that. Probably not quite as big as the previous test, so probably a little bit smaller than that. Okay. All right. Yes, Wolf.
Did you decide on the number of points for the second
I made it. Yeah, I put it in this morning. I made it 7. So there was 14 questions. So I figured half a point a question. So 7. You guys actually all turned in the Slinky Lab, so nobody's missing anything there. Oh, yeah, that's the other thing. This morning, you'll notice over on the side of the room, the turn-in stuff. It's all empty except for the quiz that Jill turned in this morning, so I have to grade that later. But so if you have stuff that is missing, and there's not a whole lot in this class, so if you have anything that's missing, please make sure you get that taken care of. As Wednesday next week is the end of the grading period, so if you have missing stuff that's adversely affecting your grade, please get that taken care of. Okay? Questions? All right. On Wednesday of this week, we started talking about the electromagnetic waves. So, quick, discuss in your small 2-, 3-person groups 2 similarities between electromagnetic waves and mechanical waves, 2 differences between electromagnetic waves and mechanical waves. Go.
They don't track energy. I'm trying to say that energy is not determined by the amplitude of the wave.
Okay, I know the difference. I think, electromagnetic waves depend on the frequency and wavelength, and
They have different frequencies and wavelengths.
depends on wavelength and frequency. Not the amplitude. Like mechanical waves, we definitely got it.
I feel you.
All right. Let's discuss. So, first things first. On the test, if you get a question similar to this one, and it says what are the similarities between electromagnetic waves and mechanical waves, and you write they're both waves, I'm not going to give you a point for that. Okay. I would give you a point though if you said something like what? What does a wave do?
They both happen because of a disturbance.
Of a disturbance that does work.
Yep.
Disturbance, I was going to say that does what, but I understand. Okay, so it does work because waves all do what?
Carry energy.
Carry energy. So if you say they're waves, meaning they carry energy, I'll give you credit for that. That's only 1 point, but okay. So they both carry energy. They both require work to be done. What else? Any other similarities we can think of? How about differences? Oh, Rachel, do you have a similarity, or you want to read? they do not transfer matter. So we're transferring energy without transferring matter. That's true in both cases as well. Okay? All right, how about some differences? Emily?
Electromagnetic don't need medium.
Electromagnetic does not need medium to travel through, mechanical does. It's probably the biggest difference. What else? Anybody else besides craft? Oh, Bolt's good.
The energy in an electromagnetic wave isn't determined by the amplitude.
The energy in the electromagnetic wave is not determined by the amplitude. What is it determined by? Frequency and wavelength, which are related to one another. Okay?
All electromagnetic waves travel at the same speed.
All electromagnetic waves travel in the same speed as long as they're in the same medium, okay? Which is not necessarily the case for mechanical waves. Okay? All right, good there? Okay. When we left off on Friday, that's not where we left off.
Electromagnetic waves.
Right there, right? Is that where we left off? Okay. So with electromagnetic radiation, we got to the point that all electromagnetic waves travel at the same speed. We discussed that speed on Wednesday, right? It was really, really fast. 3.00 times 10 to the 8th meters per second if you're talking about an electromagnetic wave traveling through a vacuum, which most of space is a vacuum. Okay? Here, right, they have different frequencies and wavelengths, and those different frequencies and wavelengths relate to how much energy those waves carry. What we find out is that there are many, many, many different types of electromagnetic waves out there. They all differ in frequency and wavelength, and that means that they all carry different amounts of energy. All of the frequencies of electromagnetic radiation we refer to as the electromagnetic spectrum. So rather than just this, let's take a look at some pictures. Okay? Which I think you have these pictures on the back of your outline, yes? No, you don't. All right. So this picture here is a pretty good representation of the electromagnetic spectrum. So you'll notice the blue bar that kind of runs through the middle, wavelength, and then the green bar that says frequency. Notice on the left end over here, long wavelengths, low frequency, because how are wavelength and frequency related to one another? Inversely related. So a long wavelength means it's big, but a low frequency means it's, if this is big, this one should probably be small, right? But over here, short wavelengths, right? Small wavelengths, high frequencies, okay? This is important because, Bull, as you told us before, what is the frequency and the wavelength going to tell us about these different waves? The energy of what they're carrying, right? Okay? So, if we look over here on the left-hand side, right, radio and TV waves, we use these for communication, right? We send this energy from one place to another. It could be, satellite TV, or it could be astronauts communicating with each other, or it could be us listening to Thrift Shop on the radio, whatever it may be, okay? So, these waves, though, you'll notice here, right, they're real long, they have very low frequencies. Now, low frequency is relative, all right? If you look at the dial, right, when you put whatever station's on, okay, that was 99.1, but it's 99.1 megahertz. Okay? Mega is a prefix that means million. So it's 99.1 million hertz, meaning that there's 99.1 million waves that go by every second. Okay? Yeah, it's a lot, right? But in relation to the other waves, that's a very low frequency. Okay? As you go up the electromagnetic spectrum, the next one we come across is microwave and radio waves. What do we use microwaves for?
Cooking food.
Mostly heat, okay? But do these waves, microwaves, have more power, more energy than radio waves? A little bit. What can we do with microwaves? Cook your Hot Pocket, right? If you sit your Hot Pocket down next to your radio, will it get cooked?
Yes.
No.
Yes. After a while, maybe.
It'll thaw, but it won't get
Yes.
cooked. You know what I'm saying? Those are two different things. Alright? So, next, infrared. There, we're giving things off like this is a lot of heat as well. Okay, a lot of heat energy energy is transferred as infrared. Not that it happens a whole lot anymore, but a lot of times, like in fast food restaurants, or what's a good example? They don't do it anymore because it's kind of gross. They used to just kind of like cook the food beforehand and sort of set it out on the plate, set it out on the counter and keep it warm. Okay, a lot of places don't do that anymore because it's kind of disgusting. But anyway, like if you ever been to some CC's, okay, like CC's,
Okay,
you know,
I
they
had
have like.
I
Oh wait, this is not a time for a CC story. So CC's has a real long buffet, right? And they got those lights right above the buffet, like the whole way. Those lights are there. Why? They're trying to keep the pizza warm, right? Those are a lot of infrared radiation, all right? Now, right in the middle, actually not right in the middle, but in the middle, right, there's this small little sliver, and you see it's kind of like fanned out here, of visible light. This is the stuff that our eyes are sensitive to. Does that mean none of this stuff ever happened? No. This stuff is happening all the time, all right? But your eyes don't pick it up. Your eyes are only sensitive to this little sliver of electromagnetic radiation that we call visible light, okay? Now, can we make it so that we can detect other kinds of electromagnetic radiation and sort of see what's going on? Yeah, we can. Have you ever seen an infrared camera, like heat vision, right? You ever watched Predator before? Anybody seen Predator before? All right, yeah, I mean,
Ghost hunters.
you know,
Ghost hunters.
what?
The ghost hunters.
Yeah. So, that infrared radiation is there all the time. Your eyes just don't pick it up. Here, ultraviolet, a little bit past the visible, okay? This radiation is hitting you all the time. Your eyes don't pick it up, but it happens. What do ultraviolet rays have the energy to do? Give you sunburn, right? Remember, they're all carrying energy. They have the ability to do damage. This stuff over here, maybe cook food. This stuff over here gives you sunburn. What about X-rays? How much energy do X-rays have?
A lot.
A lot. Enough to go straight through most parts of you, right? Without even stopping or slowing down, or I should say slowing down, but they have enough energy to go through you, right? Most parts of you, okay? But what else can they do if you're exposed to too much of it? They can give you cancer, right? They can kill you eventually, okay? Just like when you go to the dentist, right? When you go to the dentist and get your X-rays, so what do they do to you first? They give you that big heavy apron, right? Okay? And then the lady, sorry, I shouldn't stereotype like that, the dental hygienist that takes the X-rays, right? Before she takes the X-rays, where does she go? She's like, I'm going to get out of here right now because these are really powerful, a lot of energy coming from those rays out of the X-ray machine, okay? Is it enough to hurt you? Repeatedly, yes, but you don't take 10 X-rays a day like the hygienist does, right? If you're in a situation where you could be exposed to those large amounts of radiation, large amounts of energy, right, you get out of there. You don't stand there, okay? Yes, Ryan?
I'm not sure if this is true, but I've heard that if you take like 21 cross-country flights, it's like equal to the radiation of an X-ray.
A lot of our atmosphere does a good job of filtering out some of those different types of radiation, those different types of electromagnetic waves, because of like magnetic poles and things like that. But as you get higher and higher up, you're exposed to a little bit more. So yeah, that is, I don't know if that number is true, but you do get exposed to it a little bit more. Now, is it enough that you're going to end up with cancer? Maybe, maybe not, but you know, I think it's more of a scare tactic kind of thing. But yes, Steve?
They're similar to X-rays. The ones just for your teeth, those actually aren't as powerful as like a TV.
Couldn't be.
Yeah, the amount of radiation that they give off.
It's a very short burst, yes, but it's still, those rays themselves are powerful enough to go through your skin and through your gums and stop at your teeth. It's a very small amount of radiation, but that radiation is powerful.
Yeah.
Okay. Over here on the far side over here, gamma rays. Look, high frequency, very short wavelength. One of the possible demise of the Earth that comes out is called a gamma ray burst. Anybody ever hear of a gamma ray burst? Right? When things explode out there in space, you know, stars and stuff like that, they give off a lot of energy. That energy, a lot of times, comes in the form of gamma radiation. If we are, you know, in the direct path of this gamma radiation, it can cause some pretty severe damage here on Earth, right? This is energy, the ability to cause change, right? I mean, look what it did to the Hulk. Right? I mean, you know, so, there you go. Yes.
Is that like the like with Chernobyl?
In Chernobyl, yeah, we're up in this sort of area over here, yeah. The energy that a nuclear reaction gives off a lot of times is in this range of gamma radiation. So you're talking, yes, correct, you're talking like, I mean, when we're talking about nuclear bombs and stuff that's giving off a lot of energy, a lot of times it's in the form of gamma rays. So, quite good.
Is there anything past gamma radiation?
I think that gamma radiation, there are not like, you can read a book and it'll say between this frequency and this frequency, but I don't think there's not real rigid cutoffs. I don't think, I think we'd just carry on gamma radiation at that point, you know, and say that the rest of it is gamma radiation. Because really it's just like high energy waves, basically. Yeah. All right, yes, Beaver.
I'm not sure exactly what he said, but like, is there something more, like, is there something that we know is the strongest form of gamma radiation that there is?
Like I said, this is a range, you know, and I think if we discovered radiation that was of a higher frequency carrying more energy, we probably just would extend the gamma ray category and include it into that. Because really, it doesn't matter what you call it; it's more about how much energy is it carrying. No, that's more like it gives you like because your eyes focus a little different on things that are close versus far. It can cause some changes in your eyes if you do too much. But you know, if you get like the amount of radiation you get exposed to, the amount of energy you get exposed to from a TV, because those waves aren't real energetic, it's not, you know. But just from a general health standpoint, you probably shouldn't watch TV like 12 hours a day, you know. Right? Play 60, right? Get up and move, hour a day. Right? Yeah. So. All right, we good there? Okay. On your sheet, right? These 6 categories here, you'll notice that there's some arrows, right? Increasing wavelength, decreasing frequency, increasing energy, right? Make sure you have those filled out in order. All right. With that being said, let's turn our focus towards a specific type of electromagnetic radiation or a specific type of electromagnetic waves that we call visible light.
It's free.
Okay. Yeah. Yeah, those arrows on the side, yeah. All right, so yesterday, we watched the Magic School Bus. Miss Frizzle has her light video, or her light pinball game, right? What's the first thing that happens in the light pinball game? Scrap, good.
She launches like a ray of white light.
She launches let's say a burst of white light, okay? And that burst of white light bounces off of a mirror, and then went through a what? A prism. And then what happened to it when it went through a prism?
Rainbow.
Rainbow, right? It splits into its different colors. We refer to that idea as dispersion. Okay? That first, as light passes from one medium to another, in the case of the video pinball game or a prism, that would be going from air to glass, the speed of the wave changes and refraction occurs. Okay? And that causes the light waves to bend. But what we find out is that the frequency or the wavelength, because those are related concepts, right? The frequency and the wavelength of those waves determines how much they bend. Shorter wavelengths bend more than longer wavelengths. If it's got a shorter wavelength, what does that mean? It has a what? A higher frequency. So higher frequencies will bend more than longer, or more than smaller frequencies. Okay? Good with that? This is true of all waves, not just light waves. So if you take a look here, here's a picture. This is a picture of some water waves, and it's made in what we call a water table. It's basically just a glass bottom table, and you shine a light up through the bottom of it, and you can see different areas of shadows and non-shadows. These are the different waves. First, which side has the higher frequency waves, left or right? I'd go left, right? If we look here, how close are these waves together?
Oh.
These are closer, right? Meaning that these have a shorter wavelength but a higher frequency. As you look, there's like a line that kind of comes right here, happens when those waves hit that line? Are they straight? No, they're bending, right? What do we call this? This is refraction, okay? But if you notice, right, this one here, meh, and then it bends about this much, right? But this one, orange right here, right? This one bends like that much, okay? It's a subtle difference, but the one on the left, the higher frequency waves, will bend more than the lower frequency waves. These are water waves. This isn't light. This is a phenomenon that happens with all waves, not just light. But for light, that leads us to a certain thing. Different colors of light have different wavelengths. And so the different colors will bend different amounts. Because they all bend different amounts, whereas before they were all together as white light, if they all bend different amounts, now you see them all individually, right? And it gives us this lovely little thing right here, right? Like they were talking about in the video. It's just, sorry, man.
It's like pink.
Like they were talking about in the video yesterday. The colors always split up in the same order. It's always red, orange, yellow, green, blue, violet, right? Because they all have different wavelengths, meaning that they all bend by different amounts, but they all bend by different amounts the same way each time they go to the prism. Okay? Notice, your violet bends it's purple. Your violet bends the most. Why does it bend the most? Based on what you just saw, or what we just wrote down, what could you tell me about the wavelength of violet? Short. Okay? It has the highest frequency and the shortest wavelength, right? So, but red, right? So clearly that means that red would have the highest wavelength but lowest frequency, okay? So red has the longest wavelength, so it bends the least. But violet has the shortest wavelength, so it bends the most. And then in between, they just sort of all fill in. But they always bend in that order because that's how much, they always show up in that order because that's how much they bend when they go to the different wavelengths, right? This is called dispersion. All right, it's good there? Say again. Yeah, indigo kind of gets phased out, kind of like Pluto. You know, like, I mean, back in the old days it was all right, but now it becomes a little more sophisticated. Yeah, there's really not another color in between blue and violet. Like, I always looked at it and I'm like, there's no difference between this and violet anyway. Like, you know, that's what I always thought. All right. So let's talk about. Let's talk about this leaf, right? So this leaf shows up as green, and it shows up as green out there in the real world, and then it shows up as green bouncing off of this board. Okay? A couple of different reasons why. Certain materials that are out there reflect certain colors of light and absorb other colors of light. Okay? This leaf is green when you look at it outside because it reflects green light. It absorbs all the other colors of light. Okay? And you saw this yesterday in the Magic School Bus video, right? By certain colors of light bouncing off of certain things in the pinball machine, with other colors of light not bouncing off of those different color things. All right, this is an interesting discussion, but because of the schedule that we're on, we're not going to get to have it at this point in time. If you would please, can you finish those up over the weekend, and then on Monday we can address any questions, all right? If you have questions about tests, write me an email over the weekend. Yes, sir. Yes, sir.
Bigger points.